Welcome to this presentation. Today we are again discussing the question and the answers in thermochemistry. Remember last time we ended on question 39. Today we are starting on question 40. Question 40 is saying, using equations, explain how the internal energy, heat, work done, and the final temperature are calculated for adiabatic processes. They are also asking derive also the pressure volume relationship in adiabatic processes. So we need to use the equation to explain how the internal energy, the heat, work done, and the final temperature are calculated for adiabatic processes. And also, they're asking to derive the pressure volume relationship in adiabatic processes. Let's see the answer. So now, what is an adiabatic process? Remember, we have seen that an adiabatic process is a process in which there is no addition of heat, nor heat is released. So in this adiabatic process, no addition of heat and no heat is released. So that means that Q, which is the heat, is 0. So in a adiabatic process, we have Q which is equal to 0, or the change in the heat, dQ, is equal to 0. So here, no heat is added and no heat is released. The change in the heat, delta Q, is equal to 0, or Q is equal to 0. Again, in these adiabatic processes, that me remember, we have the equation in which internal energy is equal to Q plus W. This is the heat plus the work done, or the change in internal energy is equal to the change in the heat plus the change in the work done. Then we know for a adiabatic process, this Q is 0. Delta Q is 0 in the adiabatic process. If we can then replace Q or delta Q by 0, then you get the term that the internal energy is equal to the work done for adiabatic process, or the change in internal energy is equal to the change in the work done for adiabatic process. That means we'll be using this equation to derive the heat, internal energy, and work done, and the final temperature for adiabatic processes. What you need to know, what you need to understand is that the internal energy, or the change in internal energy, is equal to the change in the work done. And remember, we have derived that this term, internal energy, is equal to NCVDT. That means internal energy is equal to the number of mole times the heat capacity at constant volume times the change in temperature. That means the work done is also equal to NCVDT, because the change in the work done is equal to the change in internal energy. That is D is equal to dW. So dQ, which is the heat released or the heat which is absorbed by the system. So either the heat can be released or can be absorbed by the system, but in a adiabatic process, this dQ, or the change in the heat, is 0. And what is the dW? dW is the mechanical work. Again, either the work is performed by the system or the surrounding perform the work on the system. So the dW then is the work either performed by the system or performed by the surrounding on the system. So in a adiabatic process, we have, it can be either an adiabatic process which is expanding, a system which is expanding adiabatically. In that case, we have an expansion, increasing the volume, but the dQ, or the heat, is 0. In that case, we have adiabatic expansion. An adiabatic can be also a compression, where the gas is compressed, the volume is reduced, and at delta Q, which is equal constant, delta Q is equal to 0. In that case, we have adiabatic compression. So we have two different types of adiabatic process. We have adiabatic expansion and the adiabatic compression. So that is, so far we have expansion and compression. And remember, we have seen that also we might be having the adiabatic reversible or adiabatic reversible. And in all these conditions, we need to find the work done and the heat. So in adiabatic expansion or compression, so we can see that the du, which is internal energy, the change in internal energy is equal to the work done, and in this case we can behave expansion, and when you have the expansion, remember the work done is negative because the system is doing the work. The work done is negative, and delta U is also negative because the system is doing the work. The system is losing the internal energy to do the work. That's why the work done is negative and the internal energy is negative. And the du is equal to NCV dt. Because you have seen that the dq is equal to 0, that means automatically du is equal to NCV dt. So that means for du to be negative, that means the T2, the final temperature, is less than initial temperature. If the final temperature is less than initial temperature, in that case, the change in temperature will be negative. Then we have the internal energy, which is negative. In expansion, there is a decrease in the temperature. The final temperature is less than the initial temperature. Then we might be having also the compression. When you have compression, adiabatic compression, the work done is positive because the system, the surrounding is doing work on the system, and this work is stored as the internal energy. So that means there is an addition of internal energy. The work done is positive, and the internal energy is also positive. That means the du, which is equal to NCV dt, that means the temperature is increasing, the final temperature is higher than the initial temperature, then the change in temperature, it will be positive. In that case, we have the internal energy, which is positive. So far, adiabatic process can be either expansion or can be compression. Now, in adiabatic process can be also reversible and irreversible. And remember, in adiabatic process, no heat is added, the gas expands and it does the work. During adiabatic expansion, no heat is added, the gas expands and the gas does the work. So that means here we can explain why the temperature decreases when you are in adiabatic expansion. There is no heat, no external heat which is added, and the system is doing the work. That means the system is using its own internal energy to do the work. That is the reason why the internal energy decreases and the temperature decreases during adiabatic expansion. In order to perform the work, the gas has to use some energy in adiabatic expansion. So no energy from the surrounding is entering the system. That means for the gas to expand, the system uses its own internal energy. The system is using its own internal energy to do the work. So that means during expansion, the internal energy is decreasing. And remember, the internal energy is a function of temperature. Because the internal energy is a function of temperature, if the internal energy is decreasing, automatically the temperature also is decreasing. That's why you can see that in expansion, internal energy is negative, the work done is negative, the temperature is decreasing. Now, during the adiabatic compression, we are compressing the gas, the work done is done from the surrounding to the system. That means that work done, which is coming from the surrounding, is going to be stored as internal energy. And this work is stored by the gas in the form of internal energy. And the internal energy is a function of temperature. If the internal energy is increasing, that means the temperature is also increasing. That is the reason why in adiabatic compression, we have the internal energy which is positive, the work done which is positive, and the temperature which is increasing in adiabatic compression. So I was telling you that in adiabatic expansion or compression, we might be having either reversible or irreversible. We have seen what is the difference between reversible and the irreversible reaction. When you have an expansion, it can be either an expansion which is reversible or irreversible. When you have a compression, you might have a reversible compression and or the irreversible compression. So when an expansion or compression is moving slowly, so remember we have seen that in that case we have a reversible process. A reversible process is a process which is going slowly, and the irreversible process is a process which is going faster. Then when an expansion or compression is moving very fast, in that case we are talking about irreversible process. So remember last time we have discussed all these concept of reversible and the irreversible, and what are the differences between the two processes. We have also seen that the magnitude of work in reversible adiabatic expansion is greater than the magnitude of work in irreversible adiabatic expansion. So we have seen that in irreversible, adiabatic compression, when you are compressing the gas in irreversible process, the work done, the magnitude of work is greater than the magnitude of work in reversible adiabatic compression. Here we have reversible expansion, and we have irreversible expansion. When you are in reversible adiabatic expansion, we have more magnitude of work as when you are in irreversible adiabatic expansion. One is the reversible expansion, another one is the irreversible expansion. Then when you have reversible adiabatic expansion, we have seen that you have more magnitude of work as when you have irreversible adiabatic expansion. Again, you have seen that when you have compression, irreversible adiabatic compression is the one which has a higher magnitude of work as compared to the reversible adiabatic compression. We have seen this in the last time. Now we need to consider these two cases, reversible and irreversible. So let's see how do you determine the work done in reversible adiabatic process, whether you are having reversible adiabatic compression or whether you are having the irreversible adiabatic compression. How do you calculate the work done? Here we are going to see how do you calculate the work done in a reversible adiabatic process. So the formula that will be demonstrated here, it will be used to calculate both reversible expansion and reversible compression. We are starting with reversible. Then after reversible, we will move to the irreversible. So we have seen that the dQ, because we are in adiabatic, dQ is equal to 0, and du, internal energy, is equal to the work done. That's the reason why we want to calculate the work done. What are the formula that are used to calculate the work done for reversible adiabatic process? Remember, the work done, the general formula for the work done is equal to minus the external pressure times the change in volume, minus the external pressure times the change in volume. And if you remember, we have seen that an irreversible process is a process which is occurring slowly. We have seen that the external pressure does not much differ with the pressure of the system or the internal pressure. That means rather than using the external pressure, we can use the pressure of the gas, internal pressure, because here in reversible process, because the process is in equilibrium with the system, the external pressure is in equilibrium with the pressure of the gas. In that case, the external pressure is not constant. So then in a reversible adiabatic process, we don't use this external pressure which is not constant, but we use the pressure of the gas. So we have seen that the pressure of external pressure is not constant in a reversible adiabatic process. The external pressure is approximately equal to the pressure of the gas. That is the reason why in the calculation for reversible process, we use the pressure of the gas rather than using the external pressure, because the external pressure is not constant and it is approximately equal to the pressure of the gas. That is the reason why we are using the pressure of the gas. So the work done in a reversible process is equal to the pressure of the gas times the change in volume. So the du is equal to dq plus dw, and the du is equal to 0, plus dW. That means du is equal to dW. Then the work done, which is reversible, the change work done reversible, is equal to du, which is equal to NCV dt. So we have seen that this formula applies to either when you are in reversible or irreversible process. You have the work done, reversible is equal to du, is equal to NCV dt, is equal to minus the pressure of the gas times dV. And from this formula and this formula, we are going to derive other formula to calculate the work done in the reversible adiabatic process. So that means the work done in reversible is equal to NCV T2 minus T1. This is the change in temperature. So now we can replace the CV to get the first equation to calculate the work done. We can replace the CV here to get the equation to calculate the CV work, the work done. Remember, we have seen that the relationship between CP and CV. From that relationship, we can determine CV. We have seen that the CP minus CV is equal to R. Then we can determine that the CP is equal to CV plus R. If we can divide CP over CV, so we are dividing the CV to each term. Here we get CP over CV. Here we get CV over CV. Here we get R over CV. Then this is the gamma, remember, equal to CV over CV. This is 1 plus R over CV. So then we know we have derived that gamma is equal to 1 plus R over CV. So we have demonstrated this relationship before in previous courses. So that means gamma minus 1, if you can take this one here, gamma minus 1 will be equal to R over CV. Then CV, this CV will be equal to R over gamma minus 1. That means we're going to replace this CV, the CV here by R over gamma minus 1, so that we can get the first equation to calculate the work done in reversible adiabatic process. Here we are. So we have replaced the CV by R over gamma minus 1. So T2 minus T1. So then we can multiply. That will be NR T2 over gamma minus 1 minus NR T1 over gamma minus 1. This is the first equation to calculate the work done in reversible adiabatic process. Then to get the second equation, we can replace T to get the second equation to calculate the work done. We are replacing the T. So by using the formula, remember, so we have, this is the formula that we have, and we're going to replace this T by their value. We know PV is equal to nRT. The T, the temperature, is equal to PV divided by nR. That means the temperature will be equal to PV dividing with nR. Hope that you are getting. So PV is equal to nRT. That means T is equal to PV over nR. Then that means T2 is equal to P1 V1 over nR, and T1 is equal to P1 V1 over nR. Then we are going to replace in the equation. So we get nR over gamma minus 1, P2 V2 over nR. This is T2 is equal to P2 V2 nR minus P1 V1 over nR. We are replacing. Then so here we have the term nR. We can cancel them. nR, then we cancel them. So we remain with the final equation where we have the work done in reversible process is equal to this one. So this is the second formula to calculate the work done in reversible adiabatic process. We are still in reversible adiabatic process. Now we have seen two equations. The first equation we have replaced CV. The second equation we replace the temperature. So then you have P2 V2 minus P1 V1 over gamma minus 1 as the second equation to calculate the work done in reversible adiabatic process. So the dQ, the heat is equal to 0. So the work done, you have seen the internal energy is equal to NCV dt, and you have seen the two formulas to calculate the work done. So we are remaining with the how do you calculate the final temperature, and how do you derive the relationship between pressure and volume in reversible adiabatic process. Let's see how do you calculate the final temperature in reversible adiabatic process. So remember, still we are going to use the internal energy is equal to NCV dt. So we know that the work done also is equal to minus P dV. This is the pressure of the gas times P dV. And remember, for the reversible adiabatic process, you don't use the external pressure. External pressure is not constant. You use the pressure of the gas. That's the reason why we are deriving that work done is equal to minus P dV. This is P, this is the pressure of the gas. So we can equalize the two formula. So change the P, then rearrange the equation and integrate to obtain the first equation to calculate the final temperature. That's what you are going to do. We are going to change the P. We are going to equalize the two equations. NCV dt is equal to minus P dV. We change this P, then we rearrange the equation and integrate to obtain the first equation to calculate the final temperature. Let's go. So here we know P is equal to nRT. That means P is equal to nRT over V. So then we replace this P here by nRT over V. We get here, we are replacing the P by nRT over V. So we are rearranging the equation. So we can take this V, we can take it here. So get NCV dt times V times this V is equal to nRT dV. So we are still rearranging our equation. So NCV dTV is equal to minus nRT dV. So then we can divide this T here. We get NCV dTV over T. We are dividing this T here. Is equal to minus N minus nR dV. This is this T that we have divided here. Again, so we can rearrange the equation, have NCV dt, can have NCVV dt over t. So we are putting this dt over t aside, minus a r dv. So then you can say that dt over t is equal to minus nr dv over ncv v. So this is the equation. dt over t is equal to this one dividing with this one. So dt over t is equal to minus nr dv over ncv times v. We are still in the rearrangement of the equation. Then dt over t plus nr dv over ncv times v is equal to 0. So you can get either this one is equal to this one minus r cv dv over v. You can see that this n, you have cancelled them, the two n, they are the same. Or you can get dt over t plus a dv over cv times v is equal to 0. So then we have this equation. We can get this v here. Can get here we have v. Can get this v here. That's means v over t, and push this dt here. V over t is equal to minus r cv dv over dt. So after getting v over t is equal to minus r over cv times dv over dt, then we know that the cv here we can replace it by its value. Remember, we have seen that cv is equal to r over gamma minus 1. R over cv, this is the r over cv, is equal to gamma minus 1. Then you can replace this r over cv. Rather than replacing only the cv, you can replace this r over cv by gamma minus 1. V over t is equal to minus, so there is minus here, gamma minus 1, dv over dt. From this equation, you can see that the T, the temperature and the volume are inverse. There is an inverse relationship between the temperature and the volume. That means also the dt over t, if we are pushing here dt over t is equal to minus gamma minus 1 dv over v. So you can see that also the dt and the dv are inverse. So the dt and the t, we have dv and v. You can see that there is an inverse relationship between dt and dv. So here temperature and volume are inverse, they have inverse relationship, and remember also the dt has an inverse relationship with dv. If you can check, remember we have seen that during an adiabatic expansion the volume is increasing and the temperature is decreasing. That's the inverse relationship. During adiabatic expansion, the volume increases, the temperature decreases. Then during adiabatic compression, the volume decreases, the temperature is increasing. There is an inverse relationship between temperature and the volume during adiabatic processes. That means also there is an inverse between the change in temperature and the change in volume. So after rearranging, then we need to integrate to find the equation to calculate the final temperature. So we have dt over T is equal to, this is the equation that we have. We can get dt over T plus, can you push this equation here, plus gamma minus 1 dv over v, dv over v is equal to 0. Then we can integrate the equation on both sides. We are going to put the integration here, dt over T plus gamma minus 1 dv over v is equal to integration of 0. So then remember here we have, this is integration dt over T plus integration of y of gamma minus 1 dv over v. So here integration, this part, we also integrate this part is equal to integration of 0. When you are integrating constant, this is a constant, you get the constant. That means integration of dt over T plus gamma minus 1. Here we are putting gamma minus 1 outside of the integration because we have a constant. Dv over v is equal to integration of 0. So this is ln dot t. Remember the integration. So you cover the integration in mathematics. This will be equal to ln t. This will be equal to gamma minus 1 dv over v is equal to integration of dv over v is equal to ln of v equal to constant. Integration of the constant is a constant. Now we have ln t plus gamma minus 1 ln v is equal to constant. We are here ln t plus gamma minus 1 ln v is equal to constant. Ln t, this you can push this one here is equal to ln v power gamma minus 1 equal to constant. I'm using the properties of logarithmic and the integration. That's what you have used. Then if you are addition, the property of logarithmic, the ln, the property of ln. So we have the ln tv gamma minus 1 is the same as we multiply this t times v power gamma minus 1. Remember the addition is the same as multiplication. ln t times v gamma minus 1 is equal to constant. So remember also in mathematics, when you have the e power ln x is equal to x, then if you can apply here e and also you put e, in that case you have e power ln tv gamma minus 1 is equal to e power constant. Then that means we cancel this one, we have ln, this one it will remain for this one will cancel. tv gamma minus 1 is equal to constant. tv gamma minus 1 is equal to constant. That is what it means that t1 v1 gamma minus 1 equal to t2 v2 gamma minus 1. So now from this formula we can calculate the final temperature, which is t2. t1 v1 gamma minus 1 is equal to t2 v2 gamma minus 1 after integration. So don't get bothered with the integration. You can just get the final temperature. This you can determine the final temperature by only memorizing this final equation. If you don't bother, students sometimes they don't like mathematics. If you don't want to go through all this demonstration and integration, just make sure you get the final temperature, the final equation. T1 v1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. Then from this equation we can change the volume to obtain the second equation to calculate the final temperature. That's the first formula to calculate the final temperature, but we can change the volume. PV is equal to nRT. The volume is equal to nRT over P. Then we can change this volume and we change also this volume to get the second formula to calculate the final temperature. T1 here we replace with the V. This is V1 will be equal to nRT1 over P1. V1 is equal to nRT1 over P1 power gamma minus 1 equal to T2 nRT2 over P2 power gamma minus 1. So we are replacing this V by this formula. So can you check now? We have T1. We have NR. See how we can cancel this one and this one. We cancel them, then we remain with T1 over P1 power gamma minus 1 is equal to T2 times T2 over P2 times power gamma minus 1. Then here, remember, we have T1 power gamma minus 1 times 1 over P1 power gamma minus 1. This is T1 power gamma minus 1 times 1 over P1 power gamma minus 1. This is T2 times T2 gamma minus 1 times 1 over P2 power gamma minus 1. Then we are rearranging the equation. Then check here, we have T1 and here T1, and all of them they are power minus 1. This is like T1 power 1, T1 gamma minus 1. Here we have P1 minus gamma minus 1. So we want to push, we have pushed this P1 at the top on the numerator. In that case, we need to change the sign of power. We have P1, then it was gamma minus 1. Then we are going to put minus gamma minus 1. Here also T2 gamma minus 1. If you want to push this one in the numerator, it will be P2 minus gamma minus 1. We introduce this minus gamma minus 1. So this is the equation that we're having. It's like T1 power 1, T1 gamma minus 1, P1 minus gamma minus 1, T2 power 1. So if then you have T1 of them, they have power, it's like to add them. So that means 1 plus y minus 1. That means here the 1 they cancel. Then you get T1 power y. T1 power gamma. Because here we add the power. So 1 plus gamma minus 1. So the 1 they cancel and then remain with T1 power gamma. Then here we remain P1 minus gamma minus 1 equal to T2. Here also we add them. They cancel T2 power. We get T2 power gamma P2 minus gamma minus 1. Hope that you are following each step. So then you get 1 minus gamma. So if you are introducing this negative into the bracket, we get here minus y plus 1. That means 1 minus y. Here we get also T2y, T2 gamma, P2, 1 minus gamma. So you can see now the final equation, the second equation to calculate the final temperature, which is T2. So we can also rearrange this equation. So remember, here we have T1 over T2 power gamma. If you can take T1 over T2 power gamma, we are rearranging is equal to P2 over P1 power 1 minus gamma. Then you have T1 over T2 gamma is equal to, we can then reverse this one. That means P1, here we have P2 over P1. If you are using P1 over P2, you need to change the sign here. P1 over P2 minus 1 minus gamma, because we have inverted this one. Rather than using P2 over P1, we are using P1 over P2. Here we need to change the sign. Then we have T1 over T2 power gamma is equal to P1 over P2 gamma minus 1. Gamma minus 1, because here if you multiply this negative and this negative will be positive, then it will be gamma minus 1. Then here we have gamma minus 1. Then you can say T1 over T2 is equal P1 over P2. Here we can divide with this one, gamma minus 1 over gamma. The same as the division. If you have this one, it's the same as if you are divide this one. So we have T1 over T2 is equal P1 over P2. We divide with gamma minus 1 over gamma. So we are here. Then we get P1 over P2. P1 over P2 it will be equal to T1 over T2. But we need to reverse this one. It's like 1 divided by this one. Because here it is power 1. then it is like 1 dividing with this one, 1 dividing with y minus 1 over y, then we need to reverse, that means it will be equal to y over gamma minus 1. Can you see here? It's like power 1. Then you are taking this 1 dividing with this term, gamma minus 1 over gamma. That means then we get P1 over P2 is equal to this one, P1 over P2, P1 over P2 is equal to T1 over T2, gamma over gamma minus 1. This is the another formula obtained by rearranging the second formula. So now, we need to calculate the pressure volume relationship. In that case, we need to replace the temperature. Replace the temperature to get the equation for pressure volume relationship. Of course, PV is equal to nRT, the temperature is equal to PV over nR. Here it will get P1 V1 over nR. Here we replace with P2 V2 over nR. Quickly we replace here and we replace here. Then we will get P1 V1 gamma minus 1. You can check here. This is also like here we have 1. Here also like we have 1. So 1 and the 1 here. So then we need to add here. That means it will be P1 V1. Here will cancel. This one will go to this one will be P1 V1 gamma, P2 V2 gamma. Then if you can divide this one, P1 over P2 is equal to V2 over V1 power gamma. So this is the equation for the pressure and volume relationship in the reversible adiabatic processes. Now we are going to go to the irreversible. The formula that we have seen, they were how to calculate the work done, the final temperature in the reversible adiabatic process. Let's see the equation that we have seen. Remember, on the first, we have seen that the work done reversible equal to NCV T2 minus T1. Then we replace the CV by its value, we get this equation. Then, after, we have also this work done reversible equal to NCV T2. Then we replace the temperature to get the second equation to calculate the work done. Remember? Then, after that, we have equalized the two equations. NCV dt is equal to minus P dV. We rearranged and we integrate to obtain the first equation to calculate the temperature. The two equations are used to calculate the work done in reversible adiabatic process. And this one is used to calculate the final temperature. Then we have rearranged this equation. Here we have replaced the volume to get the second formula to calculate the final temperature. Then we have rearranged this equation to obtain this one, P1 over P2, this one. These are the three equations that can be used to calculate the final temperature. If I'm talking final temperature, I'm talking about the calculation of the T2, which is the final temperature. Now we have also replaced the T so that we can get this last formula for pressure volume relationship. The formula to calculate the final temperature, the formula to calculate the work done in reversible adiabatic process, and the pressure volume relationship. So let's move quickly to the work done in the irreversible adiabatic process. Remember, in the irreversible adiabatic process, we have a very fast process and you have a constant external pressure. In this case here, we are going to use the external pressure because the external pressure is constant in the irreversible adiabatic process. In irreversible adiabatic process, we use the external pressure. External pressure is always constant, and in this case, the work done in irreversible is equal to minus external pressure times the change in volume. Remember, in irreversible, we didn't use the external pressure, we have used the pressure of the gas. Again, the formula is the same. We know that the work done in irreversible is also equal to du, the internal energy, which is equal to NCVDT, because the dq, the heat, is equal to 0 in adiabatic process. Now we are going to derive other formula by relying on this formula and this formula. So we know that the du irreversible is equal to minus pressure external dV is equal to minus external pressure V2 over V1. So you can replace the volume to get the equation to calculate the work done. How do we replace the volume? We know PV is equal to nRT. This means V will be equal to nRT over P. Here, that means V2 will be equal to nRT2 over P2, and here V1 will be equal to nRT1 over P1. Let's replace it. So we replace it, P minus P external nRT2 over P2 minus nRT1 over P1. Then we get this equation. So here we are putting nR aside, then you get minus nR P external T2 P1 minus T1 P1 as the first formula to calculate the reversible, to calculate the irreversible work done during an irreversible adiabatic process. Irreversible adiabatic process, I'm repeating again, irreversible adiabatic process. We are going to use this equation to calculate this first equation to calculate the work done, and also we are going to use this one. When you have the two volume, the external pressure and the change in the volume, then you can use this equation. And when you have the external pressure and you have the temperatures, you can and you have temperatures and the pressure, you can then use this equation to calculate the work done in the irreversible adiabatic process. How do you calculate then the final temperature? The final temperature we are going to use to equalize the equation. The first one is NCVT2 minus T1. So we have also another equation which is equal to work irreversible is equal to minus external pressure V2 minus V1. Then we are going to equalize the two equation. NCVT2 minus T1 is equal to minus P external V2 minus V1. Then we can replace the CV and the volume. We replace the CV here and we replace the volumes to get the equation to calculate the temperature, the final temperature in irreversible adiabatic process. CV is equal to L over gamma minus 1 and P is equal to nRT. That means V is equal to nRT. P here we are going to replace nR. T2 over P2 here we replace nR. T1 over P1, and here for CV we replace the full R over gamma minus 1. So we do it quickly. We have replaced the CV here. We replace also the volume here. Let's see what we get. So you can see here the NR they cancel. We have NR on both terms here. The NR, we cancel them. We remain 1 over gamma minus 1 T2 minus T1 equal to minus external pressure T2 over P2 minus T1 over P1. That means then here we can get T2 minus T1 over gamma minus 1 equal to external pressure minus. So this minus is removed, but we need to change here. If you are military minus here, in this case we need to get T1 over P1 minus T2 over P2, because we have changed the sign here. It's equal to P external T1 over P1 minus T2 over P2. Because of here we have changed we have multiplied this sign inside. So here we have T2 minus T1. T2 minus T1 is equal to, we are multiplying gamma minus 1 to this side. It's equal to P external T1 over P1, T2 over P2 times the formula. So then this is, we are now replacing the CV and T to obtain the equation for the pressure volume relationship. In this case, we have NCV T2 minus T1 is equal to minus P external V2 minus V1. We are going to replace the CV and T and the temperature. What is the temperature? Temperature PV is equal to nRT. The temperature is equal to PV over nR. That means here we are going to replace with P1 V1, P2 V2 over nR, and here we replace it with P1 V1 over nR. we are replacing the temperature here to get the pressure volume relationship. So here we are replacing the CV and you have replaced the temperature. So that means you have the NR side, NR. So you can have then here the N and R. This is the NR. Here we also have NR. Then we can cancel them. So we get the P2 V2 minus P1 V1 over gamma minus 1 is equal to external pressure V1 minus V2. So that means P2 V2 minus P1 V1. Then we multiply this gamma minus 1 to this side is equal to P external V1 minus V2 times gamma minus 1. So now we are at the end. You can see the summary for irreversible adiabatic process. So for irreversible adiabatic process, we have seen that we use the external pressure, and here we replace the volume, and you get this equation to calculate the work done in irreversible adiabatic processes. Then remember, we have also equalized the two equations where NCV T2 minus T1, this is the du, is equal to minus P external V2 minus V1. This is also work done, because remember du is equal to the work done. Then here we have replaced the CV and we have replaced the volumes to get the equation to calculate the final temperature. And also we have we can rearrange this equation, the T2 minus T1, by multiplying this gamma minus 1 to this side to get also this equation to calculate the final temperature. So we have also replaced the temperature, the CV and temperature, to get the pressure volume relationship. Then we got this P2 V2 minus P1 V1 over gamma minus 1 equal to pressure external V1 minus V2. Here also you can rearrange the term by multiplying gamma minus 1 to this side. We get P2 V2 minus P1 V1 equal to P external V1 minus V2 times gamma minus 1.